In this video, we're going to talk about optical activity and specifically how it relates to chiral compounds. So, the structures of enantiomers are very similar, right? They're only different in the way that our left hand differs from our right hand. As such, they have the same physical properties. Now, they do differ significantly in the fact that they interact chemically with other chiral compounds differently, and then they also have different optical activities. And so, let's talk about what optical activity is. So we know that electromagnetic radiation consists of oscillating fields or oscillating electric and magnetic fields. And the orientation of the electric field is called its polarization. Now, normally a light source is not polarized. It consists of lots of different orientations of the electric field. But if we place that light beam through a polarizer, we can select only a specific polarization of that light, and so we block all the other ones. If we send that through another polarizer that has a different orientation, then the light that's been polarized can't get through that. So what's interesting is that when plain polarized light is passed through a sample of a chiral compound, the plane or the orientation of the electric field actually rotates. And so compounds that can rotate plane polarized light are called optically active, and only chiral compounds are optically active. Now, to look at this in a little bit more detail and actually to talk about how we might measure that, we would do that with an instrument called a polarimeter. And so uh, the way a polarimeter works is we have a light source that's not polarized. And so we initially pass that light through a polarizer, and so only one orientation, only one polarization of the light is allowed to pass through. We then have a polarimeter tube, and in the polarimeter tube we'll have our chiral compound. As the light passes through the polarimeter tube, the chiral compound causes the light to be rotated. And so by the time it gets through the polarimeter tube, it will have a different polarization, or the electric field will have a different orientation. And so we have an analyzer. This is essentially just another polarizer that we can rotate, and we keep rotating it until we can see the light. And so we know what the original polarization is. We know what the final polarization is, and so we can determine how much the polarization of the light has been rotated by passing through our sample of chiral molecules. So it turns out that enantiomers will rotate the plane of light to equal degrees, but they do so in opposite directions. Now, the degree to which the light is rotated depends on a lot of different factors. It depends on the specific compound. It also depends on the concentration of the solution. It also depends on the path length of light, right? The longer the polarimeter is, the more opportunity the chiral compound will have to rotate it. And so standard optical rotation measurements are done at a concentration of 1 gram per milliliter and with a path length of 1 decimeter. Now, if we use other concentrations or other path lengths, then we can convert what we call our observed rotation, this alpha, into the specific rotation, which is the alpha that we would have measured with 1 gram of compound and 1 milliliter of solution. So the observed rotation is alpha without the brackets. A specific rotation is indicated by putting brackets around the alpha. Typically, when we measure optical activity, we also specify the temperature and wavelength because the optical activity also depends on these variables. And so if we have two enantiomers of bromobutane, I have R2 bromobutane on the left and S2 bromobutane on the right. The specific rotation of R2 bromobutane is negative 23.1, and of its enantiomer, S2 bromobutane, it's positive 23.1. So the R and S that we've encountered before, they refer to the configuration of the chirality center. The positive and minus signs refer to the direction that the plane of light is rotated. As you can see, right, the two enantiomers rotate the light to equal amounts, but in opposite directions. And here we said that the 20 is the temperature, usually in degrees Celsius, and then this should be the wavelength. A very common wavelength to use is the D line of the emission spectrum of sodium, and that's 589 nanometers. And so if you see a D here for the wavelength, that means 589 nanometers. Now, this is sort of a note on nomenclature. When a compound rotates the plane of light in the positive direction, that's called dextrorotary, and in the opposite direction is levorotary. Now, this particular compound has an optical rotation that is levorotary at 20 degrees Celsius, but it's dextrorotary at 100 degrees Celsius. You can see the temperature greatly affects what the optical activity is. And this also tells us that there is no correlation between R and S and plus and minus. We can determine R and S from looking at the compound, but whether it's dextrorotary or levorotary has to be determined experimentally. And there is no correlation between R and S and plus and minus. And so we mentioned this on the last slide. The magnitude and direction of optical rotation cannot be predicted. It has to be measured experimentally. However, if we have a racemic mixture, and that is that I have exactly a 50-50 mixture of the two enantiomers, then the optical activity will be zero. And that's because the optical rotation caused by each enantiomer cancels each other out. Now, if I have one enantiomer in excess, so if I've got more of one enantiomer than the other, then the mixture will be optically active, but it will be less than what we would expect for the pure enantiomer. And so for unequal amounts of enantiomers, we can calculate what's called the enantiomeric excess, and we can determine this from the observed optical rotation. And so if we have a mixture of R and S 2-bromobutane, and we measure an optical rotation of negative 4.6, right, we can see that we have more of this particular enantiomer. And if it was pure, it would have had an optical activity of 23.1. We're obviously less than that. And so to calculate the enantiomeric excess, we would take our observed optical activity divided by the optical activity of the pure enantiomer and then multiply that by 100. So in this case, we'd take the 4.6 divided by the 23.1. And so our enantiomeric excess is 20%. This means that I have 20% more of this enantiomer than I do of this one. Now I have another video where we do some calculations on specific optical activity and on calculating enantiomeric excess.